Today we will discuss about the force between two parallel current carrying conductors. Now, with all the discussions we have had so far, we are clear about two things. One, whenever there is current flowing through a conductor, it generates a magnetic field around it. Two, whenever a conductor carrying current comes under the influence of a magnetic field, then the current carrying conductor experiences a force, either a force of attraction or a force of repulsion. So these two things are evidently clear to us. The first case happens due to the unification principle that underlies the electric fields and the magnetic field. The second principle happens because of the interaction of two magnetic fields. One, the field that's the source field which is influencing the current carrying conductor, and the second, the field generated by the very conductor which is carrying the current. The interaction of these two magnetic fields produces a force of attraction or repulsion. So now, if I consider two conductors, two straight conductors carrying some current each, and they are placed at a certain distance from each other, then the idea is to find out how would the two get influenced by each other. So let's consider a scenario wherein I have two conductors. So let's say I have a thin conductor called A and another thin conductor placed parallel to it, which I'll call as B. And let's assume that I am passing current IA through the first conductor and current IB through the second conductor, and let the two of them be separated by a distance small d. Now, this current carrying conductor creates a magnetic field. Now, this magnetic field its influence will be felt by this conductor, and because this conductor is in the vicinity of the magnetic field of this conductor, it experiences a certain force. So we'll try to find out what that force is. So before that, let's find out what the magnetic field, what is the strength of the magnetic field that is being generated by this current carrying conductor A. So let's make use of the Ampere circuital law, and based on that we find that the magnetic field, let's say BA, due to the current carrying conductor capital A, is given by mu naught times IA divided by 2 pi r. R is the distance from the current element to the point of interest. So here the distance point of interest is on this conductor, and I am interested in finding out what is the magnetic field at this point due to this current carrying conductor. So this becomes 2 pi d. So this is the strength of the magnetic field being generated by this current carrying conductor at a distance d from it. So let me mark this as equation 1. Now the second part I am interested in is finding out what is the force being felt by this conductor due to the magnetic field generated by current carrying conductor A. So let me call that force as FB A, or the force on the current carrying conductor B, I will use the capital convention B, due to current carrying conductor A, force on B due to magnetic field of A. So that's what this sign convention represents. So now before we proceed, you may recall that the force felt by any current carrying conductor of a certain length L, when placed under the influence of an external magnetic field B, is given by F is equal to I L into B. So if a conductor is carrying a current I and is of length L, then it will feel a force F when placed inside an external magnetic field of strength B. So this is the equation that lets us know about the force being. So over here, if I were to write the same thing over here, the force being felt by the current carrying conductor B of length L. So what is the current it's carrying? It's carrying the current IB of length L when placed in the magnetic field being generated by current carrying conductor A. So that is BA. So if I were to substitute this particular values from equation 1 on to here, I will be getting FBA equal to IBL into mu naught IA by 2 pi D. So with a little bit of rearrangement, I will be able to write mu naught L IA IB by 2 pi D. So this is the force being felt by this current carrying conductor when placed in the magnetic field being generated by conductor A. Now what do you think is the direction of this particular force that is being felt? To find that out, let's do a simple exercise. First I need to find out what's the direction of this magnetic field being generated by A. So current is flowing from the bottom to the top over here. So when I use my right hand thumb rule and grip this conductor such that my thumb points in the direction of the flow of current, then you can see that my fingers curl around the conductor such that at this point the magnetic field is going into the board and at this point the magnetic field is coming out. So to the right of this conductor A, the magnetic field goes into the board. So now, to find out the force being felt by this particular conductor, I use Fleming's left hand rule. So in Fleming's left hand rule, if you recall, the middle finger shows the direction of current. The index finger is pointing in the direction of the magnetic field. If when these two are aligned, then the thumb will give me the force, the direction of the force being felt by the conductor. So I'll align this according to the two things that I have here. So with respect to conductor B, the current is flowing upwards. So I align my middle finger such that it's flowing upwards. Now I turn my three fingers such that the index finger points in the direction of the magnetic field. So magnetic field due to A is going into the board. So I have to place my two fingers this way. So both are aligned according to their respective entities. This represents current flowing upwards. and my index finger represents the magnetic field going inside. Then my thumb will give me the force being felt by conductor B, that is FBA is in this direction. So conductor B is being pulled towards conductor A. Now let's try to do the same exercise in the reverse way. What is the force on being felt by conductor A due to the magnetic field being generated by conductor B? So I can do a similar exercise. So if I were to find out dB, that is the magnetic field being generated due to the current flowing through conductor B, that is given by, again using the Ampere circuital law, I get mu naught IB by 2 pi d. Now if I tell it FAB, now based on the same definition, FAB will be the convention to say force on A due to the magnetic field due to current carrying conductor B. So FAB will be I A L B B. So I substitute this over here and that gives me FAB equal to mu naught L IA IB by 2 pi d, because here too I consider a length of the same specification, which is L. So FAB and FB are the same, which means to say the force being felt by both the conductors due to each other is the same. Then what is the direction of FAB? So again use the same logic to find out what is the direction of FAB. So I grip this conductor with my right hand such that my thumb points in the direction of the flow of current, and you can see my fingers are curled outside over here, which means the magnetic field due to this conductor is coming out of the board here and going into the board on this side. So since it's coming outward, now I use my left hand, Fleming's left hand rule over here. So middle finger shows the current, so current is going this way, and here the magnetic field is coming outward. So I just rearrange my fingers and you can see this coming out, and this thumb shows the force. So which means FAB is in this direction, which means both the forces are equal but towards each other, which also leads us to another important conclusion. If the two currents are uniform and flowing in the same direction across two parallel current carrying conductors separated by some distance, then the two conductors will be mutually attracted to each other. The force will be felt equally and towards each other. Now you can tell me what happens if I make this current flow downwards in this particular conductor. Obviously now the forces being felt will be that of repulsion. The two conductors will repel each other. So this is an important point to note. Whenever currents are flowing in a streamlined fashion among two parallel conductors separated by some distance in the same direction, then there's a force of attraction. When the currents are in opposite directions, there's a force of repulsion. So previously we discussed that the force being felt by two parallel conductors carrying currents will be equal, and when I consider the direction too, I can also introduce a negative sign. They will be equal and opposite. And we also discussed the fact that when they are carrying currents in the same direction, they feel a force of attraction, and when they are carrying currents in the opposite direction, there will be a force of repulsion felt by them. And we also arrived at the common expression on the right hand side, which turned out to be mu naught L Ia Ib divided by 2 pi d. Now, if I were to represent small f AB to be the force per unit length of the conductor due to the magnetic field of B, then this particular right hand side expression reduces to mu naught Ia Ib by 2 pi d, because the L and L cancel out each other, because I am taking this expression to be per unit length. So this becomes my expression. This expression is sometimes also used to define the SI unit of current, or the ampere. So to define the ampere, we'll take some x quantity of current being used for IA and the same x quantity of current being used for IB. These x stands for the standard unit of current, which then leaves me with FAB defined as mu naught by 2 pi. So D, I'll take it as a length of 1 meter, and this I will take it as 1 into 1, some standard quantity of 1 into 1, whatever that quantity is, we'll define it later. So that leaves me with mu naught, the value of which is 4 pi into 10 power minus 7 divided by 2 pi. That leaves me with 2 into 10 power minus 7. Since the left hand side is force, this comes to be 2 into 10 power minus 7 Newton per meter. So with this, we can define ampere in standard units. So ampere is that quantity of current which, when passed through two parallel extremely long conductors placed at a distance of 1 meter from each other, and which also have negligible cross section, then they both feel a force of 2 into 10 power minus 7 newtons per meter. When this happens, then the amount of current that I pass through both the conductors is said to be exactly 1 ampere each. So this is how scientists arrived at the standard definition of ampere back in 1946. And following that, you could also go on to define other units like the coulomb to be defined on the basis of the ampere. So once you have the ampere defined, now we know that current is charges per unit time. So coulomb can be defined as the total number of charges that pass through a point in 1 second when a current of 1 ampere is made to pass through a conductor.